In this episode, we're going to take on a category of problems that feels especially unsettling when you are new. The system crashes in weird ways, applications die for no obvious reason, or the same action works 1 minute and fails the next. These are the moments where it is tempting to blame randomness, but Linux systems usually behave predictably once you know what kind of failure you are looking at. The key is to separate symptoms that point to software logic problems from symptoms that point to corrupted data or unstable hardware, because the right response depends on that classification. We'll focus on what corruption means in practical terms, how kernel-level corruption differs from data corruption on disk, and why user programs sometimes crash with messages that sound scary even when the kernel is still fine. We'll also explain segmentation faults in plain language, because they are one of the most common crash signals you will see, and they are often misunderstood as a sign that the whole system is broken when the issue may be more localized. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A solid way to begin is to define corruption as the system storing or using information that is not what it is supposed to be. That can happen in memory while something is running. It can happen on disk where files live for a long time, or it can happen during transmission between components. Corruption is not always dramatic like a sudden reboot. It can be subtle, like a configuration file that looks normal but contains one bad character that changes meaning, or a library file that is slightly altered so programs that depend on it start failing. Beginners often think corruption must come from a malicious actor, but in reality it can come from ordinary failures like unstable memory, failing storage, power loss at the wrong time, or software bugs that write incorrect data. The challenge is that corruption symptoms often look like unrelated errors scattered across the system, because the corrupted piece might be shared by many programs. When you treat corruption as a possibility, you start asking questions about consistency and scope, which is the foundation of effective triage. One of the most important distinctions is whether the corruption appears to be happening in the kernel or in user space. The kernel is the core of the operating system that manages memory, processes, hardware access, and file system interaction, while user space is where normal applications run. When the kernel is corrupted or unstable, the system may panic, freeze, reboot unexpectedly, or behave unpredictably at a broad level, because the component that manages everything is compromised. When user space is the main problem, you may see specific applications crash while the rest of the system remains responsive, and the failures may be tied to a particular service, library, or dataset. This distinction matters because kernel-level instability raises the likelihood of hardware issues or deep driver problems, while user space crashes often point to application bugs, incompatible libraries, or corrupted files that the application is trying to load. A beginner-friendly mental model is to ask whether the operating system itself seems to be losing control or whether the operating system is still stable but a program inside it is failing. Segmentation faults are a classic example of a user space crash signal that sounds catastrophic until you understand it. A segmentation fault usually means a program tried to access memory it was not allowed to access, such as reading or writing to an invalid address. Modern operating systems enforce memory boundaries, so one program cannot accidentally scribble over another program's memory, and a segmentation fault is the enforcement mechanism showing up as a crash rather than silent corruption. Many beginners interpret a segmentation fault as the computer being broken, but it is often the opposite. It is the system protecting itself from a program that is behaving incorrectly. The cause can be a bug in the program, a bug in a shared library it uses, or bad input that triggers an unhandled edge case. However, segmentation faults can also increase in frequency when memory is unstable, because random bit flips can turn valid pointers into invalid ones. That is why you do not stop at the label. You consider the pattern and the environment. To triage weird crashes, you want to look for repeatability, because repeatable failures usually point to deterministic software problems, while non-repeatable failures raise suspicion of corruption or hardware instability. If the same command, the same request, or the same workload reliably triggers the same crash, that suggests a specific code path that can be investigated, and the best next thinking is to identify what inputs and libraries are involved. If crashes appear across different programs and in different contexts, especially after the system has been running for a while, you widen your hypothesis set to include memory pressure, storage problems, or kernel instability. Another powerful clue is whether the system logs show related messages near the time of the crash, because logs can reveal patterns like repeated I/O errors, driver resets, or file system warnings that correlate with the weird behavior. Even without diving into tool usage, the concept is that evidence near the time of failure is more valuable than guesses made later. A calm responder learns to treat time correlation as a primary clue because it often connects scattered symptoms into one cause. Data corruption on disk is its own category, and it can be caused by failing storage media, unsafe shutdowns, buggy drivers, or rare edge cases in the storage stack. The reason it is so disruptive is that disk data is shared and persistent, which means one corrupted file can break multiple services for a long time. For example, if an important shared library becomes corrupted, many programs that rely on it might crash or refuse to start, and the failures can look like independent issues when they are actually one underlying problem. File systems are designed to reduce corruption risk through techniques like journaling, which helps keep the file system structure consistent after a crash, but journaling is not a magic shield for every possible data problem. A file can still contain incorrect content even if the file system structure is intact. This is why a system can appear to boot and mount normally, yet still behave strangely because specific files are damaged. Understanding that difference helps you avoid the beginner mistake of assuming that if the file system mounted, data must be fine. Memory corruption is another major suspect when crashes feel random, especially when they show up in different programs that do not share much else. Random access memory, or RAM, is where running programs store their active data, and if memory is unstable, the system can behave unpredictably because programs are operating on altered values without realizing it. Some systems use error-correcting code, ECC, memory, which can detect and correct certain memory errors and can report when corrections occur, but many systems do not have that protection. When memory corruption is the cause, you might see symptoms like segmentation faults in multiple programs, unexplained decompression errors, or data that fails checks intermittently. The core idea is that unstable memory attacks correctness at the most fundamental level because everything running relies on memory being trustworthy. A beginner might assume software is always the culprit, but when the pattern crosses unrelated applications, hardware becomes a more likely explanation. The triage mindset is to treat the system as a whole and ask what shared components could cause scattered failures. Kernel instability can come from hardware issues, but it can also come from drivers and low-level interactions that operate close to hardware. The kernel must coordinate devices, storage controllers, and network interfaces, and when something at that level misbehaves, you can see hangs, lockups, or sudden reboots that do not look like normal application crashes. A kernel panic is a strong signal that the kernel hit a condition it could not recover from safely, and while panics can result from genuine kernel bugs, they can also be triggered by corrupted data structures in memory or by severe hardware faults. The confusing part for beginners is that a kernel panic message may name a module or component they do not recognize, but the practical interpretation is still about where in the system the failure happened. If the kernel is the component failing, then reinstalling a single application will not fix it, because the issue is below that layer. The right first response behavior is to preserve evidence and focus on broad categories like storage, memory, and driver interactions, rather than chasing one scary-looking word on the screen. It also helps to understand that corruption can be silent for a while, which means the system may appear healthy until it touches the corrupted portion of data. This is why a system might run fine for days and then crash when you run a particular workload, open a particular file, or load a specific library. Silent corruption is especially frustrating because it feels like the crash came out of nowhere, but it usually came from a past event that damaged data or introduced instability, such as a power interruption or a failing disk sector. In mature environments, checksums are used to detect unexpected changes in important files, and backups are used so you can restore known good versions when corruption is confirmed. The beginner takeaway is not to become obsessed with worst-case scenarios, but to recognize that data integrity is an ongoing concern, not a one-time setup. When you treat integrity as a continuous property you maintain, you are less surprised when a delayed symptom finally appears. A practical conceptual tool for reasoning about storage health is to remember that many drives can report signs of deterioration before they fully fail. Self-monitoring, analysis, and reporting technology, SMART, is one example of a mechanism where a drive tracks internal indicators that can hint at reliability problems. You do not need to know the specific indicators to benefit from the idea, which is that hardware often gives early warnings if you know to look for them, and if your monitoring is designed to capture them. The same principle applies to file systems, which can sometimes detect and report inconsistencies before they cause catastrophic failure. When you see repeated read errors, sudden remounting into read-only behavior, or complaints about metadata, those are not just annoying messages, they are signals about integrity risk. The reason this matters for Linux Plus reasoning is that you want to connect symptoms to the right subsystem. Repeated storage-related warnings shift suspicion away from application logic and toward the reliability of the underlying data path. Weird crashes are also sometimes caused by mismatch rather than corruption, and that distinction can keep you from looking for ghosts. A mismatch might happen when an application expects one version of a library but finds another, or when configuration changes create incompatible assumptions. Those problems can look like corruption because they cause sudden failures, but the data might be perfectly intact. The difference often shows up in repeatability and in scope because mismatches tend to produce consistent failures tied to specific programs or services. Corruption, especially hardware-driven corruption, tends to produce broader and less predictable symptoms. This is why a strong triage approach includes asking whether the crash began after a known change, such as an update, because a change-driven failure is more likely to be a compatibility issue than a spontaneous corruption event. Beginners sometimes skip that question and jump straight to deep diagnostics, but the change timeline is one of the highest value pieces of evidence you can use. When you learn to reason with timelines, you reduce your search space dramatically. Another concept that helps you stay calm is to distinguish between the symptom of a crash and the cause of the crash. A segmentation fault is a symptom that says the process hit an illegal memory access, but it does not tell you why that happened. The why could be a bug, a bad library, corrupted input data, or unstable memory, and those causes have very different fixes. Similarly, a kernel panic is a symptom that the kernel could not continue safely, but the underlying cause might be storage access failure, driver behavior, or corrupted kernel memory state. A beginner often tries to treat the symptom label as the diagnosis, which leads to random fixes that do not address the root cause. A more mature approach is to treat the symptom as a classification step, then gather evidence that distinguishes between likely causes. That evidence might include whether the crash happens in one program or many, whether there are storage warnings, whether the system is otherwise stable, and whether the issue started after a specific change. From a first response perspective, the safest pattern is to prioritize actions that preserve the system state and reduce further damage while you learn more. If you suspect storage corruption, you want to avoid actions that cause heavy writes before you understand what is happening, because excessive writing can make recovery harder if the device is failing. If you suspect memory instability, you want to avoid trusting results from complex operations that depend on correctness, because unstable memory can make diagnostics lie to you. If you suspect a software bug, you want to capture enough context to reproduce it, such as what inputs trigger it and what environment details are consistent. The theme is that good triage reduces risk while increasing information. You do not have to rush to a fix. You rush to the right classification and evidence collection, which makes the eventual fix more reliable. That is how professional incident response feels calm even when the symptom is chaotic. It is also useful to connect this topic to why Linux systems use strong boundaries between processes and enforce memory protections. When a program crashes with a segmentation fault, the system is usually preventing a worse outcome, such as silent corruption of other processes or of kernel memory. This is why you can sometimes see a service crash repeatedly while the rest of the system keeps running, which is frustrating but also protective. The same philosophy appears in file system journaling and in permission boundaries. The system is designed to contain failures. As a learner, You should treat crashes as signals that containment is working, and your job is to interpret the signal correctly. This perspective prevents the common beginner emotional reaction that everything is broken. Instead, you ask what boundary was enforced and what that tells you about the failing component. When you think this way, you start to see Linux as a system built for controlled failure, which is a powerful mental model for troubleshooting. As we wrap up, the main goal is to recognize corruption and weird crashes as a set of patterns you can reason about rather than a cloud of randomness. Kernel-level instability tends to produce broad symptoms like panics, freezes, or unexpected reboots, often tied to deep interactions with memory, storage, or drivers. Data corruption tends to cause persistent, shared failures where specific files or libraries become unreliable, sometimes showing up long after the original damaging event, and sometimes hinted at by mechanisms like SMART reporting or filesystem warnings. Segmentation faults are common user space crash symptoms that often indicate a program hit in illegal memory access, which may be due to software bugs, corrupted inputs, library mismatches, or unstable RAM, and the pattern across programs is one of your best clues. First response triage is the discipline of classifying the stage and scope of failure, correlating symptoms with timelines and logs, and taking low-risk actions that preserve evidence while you narrow the cause. When you build that discipline, weird crashes stop feeling like chaos because you have a structured way to turn them into solvable problems.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.